So we're going back to sort of the philosophy portion of this class, talking about entropy and the Clausius inequality. Um, the Clausius inequality the next assignment I'm going to give you is going to be based on this. And remember that the Clausius inequality says for an actual cycle, so we're not talking only about ideal things here. We are talking about cycles only. Um, the integral of uh, squiggly dq over temperature for the cycle around the whole boundary is less than or equal to 0. And it equals 0 for a reversible cycle. You can also express this. This is kind of hinting at something we're going to do when we get to entropy calculations, as the integral over the cycle of all the heat transfers divided by the temperatures where they're transferred at the boundary is equal to some negative constant sigma. And sigma is equal to 0 for a reversible cycle. Okay. So that's the two ways you can think of it. And then that sigma can't be negative, you know. But when we start talking about entropy, this constant that we're going to use is going to be a useful thing for us. Okay, so let's, I'm going to do an example of the kind of thing that you'll be doing with the Clausius inequality problems. Oh, one thing I want to say before I get into this, so I always give you equations on tests and stuff, and I'll still give you the Clausius inequality, and I'll give you the definition of entropy and stuff. But these are really things, to do these problems, you have to have these definitions in your head. You know, you're going to want to remember these definitions, not because they're not available on paper, but because stuff on paper is not useful when you're trying to think of stuff, you know. Okay, so let's say that we have, and before I do this, I want to point out that you can use the Clausius inequality to find the relationships between reservoir temperatures of reversible and irreversible cycles. Okay, so for example, if you have a refrigeration cycle and you know that the say you know that the hot reservoir is the same for a reversible refrigeration cycle and an irreversible. What is the relationships between the temperature of the carrots in the two, you know? And you may be able to sort of have intuition about that, but this will let you calculate that, Okay. And I'm sure, I don't remember specifically, but I'm sure there's a problem or two like that. So we're going to do an example like that right now. So let's say that you have, okay, so yeah, like say that you had, say that, so in a refrigeration cycle, the hot reservoir is the room, okay? Because it's rejecting heat from the coils in the back of the refrigerator to the room. So say you have a reversible refrigerator and an irreversible refrigerator in the same room, and the work that you're doing at the at the compressor is the same. Okay. Well, what would you guess is the relationship between the temperature inside the refrigerator? Well, you might think, you probably would think like, okay, well, a reversible refrigerator is a better refrigerator. It doesn't have friction and all those kind of things. So it's probably colder on the inside than the actual refrigerator, the irreversible one. Okay. And that's right, I think. Um, but this is a way that you can actually calculate that. You know, there's one thing to have an intuition, and there's another thing to sort of prove it mathematically. Oh, I see. There. Okay. Okay. So let's say that we have reversible and irreversible power cycles. Um, and let's say that both discharge a heat QC um, to the cold reservoir at a temperature TC. Okay, so they have the same cold reservoir temperature. Um, and let's say that both receive the same amount of heat QH from the hot reservoir. Uh, which cycle has the higher value of TH? Um, well, does anyone have intuition about how this is going to work? So think about one of those as being better and one of them works better and one of them works worse. You're getting the same amount of, uh, you're discharging the same amount of exhaust to the cold reservoir. You're gaining the same amount of heat from the hot reservoir. Which one would you guess is going to have higher, um, the higher temperature of the hot reservoir? The irreversible, right? The one that's worse, you got to shovel more coal into it to get the same effect. Okay, but now we're going to use the Clausius inequality to show that. Okay, so we expect um, TH. Uh, let's see, which do I call these? TH. So let's say we expect the TH prime uh, for the irreversible cycle. to be greater. Um, okay, so the Clausius inequality for the reversible cycle. Um, we know that the integral for this cycle of all the heat transfers divided by the temperature where it's transferred has to be equal to 0. Okay, that's the rule for the Clausius inequality for a reversible cycle. And so, what are the heat transfers at these two reservoirs? Well, there's energy coming in at the hot reservoir. So we have. So what's the energy coming in at the hot reservoir? QC or QH? At the hot reservoir is QH. That's coming in. That's why this is positive. And the temperature is TH. And then there's heat going out. Yep. So we're going to have negative QC. And what's the temperature where it's going out? TC. And this has to be equal to 0. And so we have QH over TH is equal to QC over TC. And so TH, if you do that algebra, is equal to QHTC divided by QC. Right? And now we're going to do the same thing for the irreversible. And the steps are all going to be the same. The difference is just that we have an inequality over here. So for the irreversible case, we know that the integral over the cycle of all the heats divided by the temperature has to be less than 0. Any questions about that? And so for the irreversible, I mean, it works the same. You have QH divided by, I'm calling this one TH prime, minus QC over TC. This time it has to be less than 0. So QH over TH prime has to be less than QC over TC. All of these are positive, so we can multiply and divide from both sides without changing the direction of the inequality. And so you get TH prime is greater than, because I don't know, you can follow this, right? TH prime is greater than QH TC over QC. The right sides of these two expressions are the same. And so TH prime is greater than TH. Any questions about that? Okay, so for any of these kind of things, I mean, you can do this to find the relationship between heat transfers if you keep all the other stuff the same, or temperatures if you keep all the other stuff the same in any of those three cycles, the power cycle, the refrigeration cycle, or the heat pump cycle. Okay. Um, what you need to remember for the inequality is if you're like cross multiplying and all this stuff, all the QH, the QC, the TH, the TC, they're all positive because these temperatures are in Kelvin. Okay. And so that affects the kind of math that you're doing with the inequality. Like remember, so if you have -5/4 is less than uh, 2/3, you know, when you multiply that negative and divide that negative around, you have to flip the direction of that inequality. You know what I'm talking about?
Well, why did we flip it?
What?
Why did we flip it in here?
Why did I just put that up?
No, why did you flip it?
Oh, because I just switched sides. So let me just go through these steps. I do that over and over again. Like I skip steps and then I ask if it's okay, and then I end up going back, and it all takes more time than it would have in the first place. Come on, you dummy. So we have this, and so now we'll go QH is less than TH prime times QC over TH, and then we'll divide QC over TH from both sides, and we get so we get QH TH over QC is less than TH prime, and so then I just flip which side is which.
Is that supposed to be TC?
That is supposed to be TC. You're right. TC. Okay, QC over TC. TC. So TH prime is greater than TH. Which explains why you'd rather, I mean, it's it, it's obvious intuitively that you'd want a more efficient cycle, but here's why you want a more efficient power cycle. Like if you have a power plant, you want to get rid of all those inefficiencies inside your cycle, because if you don't, you have to have more nuclear react, a stronger nuclear reaction going on or whatever to raise the temperature of the high temperature reservoir to get the same results. Okay, so now we're going back to entropy. Um, and remember the change in entropy, which is entropy at state 2 minus the entropy at state 1, is equal to the integral from state 1 to state 2 of delta Q over T all the way around the boundary. But this has to be for a reversible cycle. It actually has to be an internally reversible cycle. Okay, we've seen this already. Um, capital S is an extensive property. And the units are units of energy divided by units of temperature. Remember that these units of temperature have to be on an absolute scale. So there's never a case where you can use Celsius or Fahrenheit as units of entropy. So the SI units, the ones we're going to pretty much always use, are joules per Kelvin. You can remember that because it's like you learn all this crazy stuff about definitions or whatever. It wouldn't shock you if someone at the end was just like, just kidding. So that's how I remember that. JK, LOL. Entropy isn't a thing. In tables and websites, they give specific entropy, which is a lowercase s. I'll do it as a script s, but it's just a lowercase s. And this is the extensive entropy per mass. And so the SI units of that, are just the units of entropy divided by kilograms.
What is that symbol?
This thing?
Yeah.
That's like a cursive S. Did any of you guys learn cursive in school? Okay. Well, that's a lowercase s. So you can also, I don't know. Just somehow you have to indicate to yourself and people reading your notes that that's a lowercase and not an uppercase. Okay. S's can be confusing that way because they look the same. But this has SI units of joules per kilogram Kelvin. So now we're going to talk about the first way that we can use entropy, the first calculation we can do involving entropy. And it comes from what are called the TDS equations. And one thing, so much of this class is about learning under what conditions you can apply this, under what conditions you can apply this. This is one of the rare things that always applies. So these are always applicable. So you like when you have something like that. And they give relationships between the changes or the change in specific entropy and changes in other properties. And there are two different TDS equations. Usually you just use one depending on what properties you're dealing with. So the first one says TDS is equal to du plus PdV. And the second one says TDS is equal to d little h minus v dp. So those are the TDS equations. So I said these are always applicable. They're like general equations, but the problem is, okay, they're general, but you can't integrate these to get answers until additional assumptions are made. And those are just going to depend on your specific case. Okay. Okay, so let's see an example. So let's say we want to calculate an expression for the change in specific entropy for an incompressible material. So like a liquid. Well, what do we know about incompressible materials? Let's think back about that. You can think of the definition of an incompressible material as like the density or the specific volume is constant, can't change. That's like the definition. So V is constant. Equivalent to that is that the density is constant. So at the top of the ocean and the bottom of the ocean, the density of the water is basically the same. The only change, small change, is due to slight change in temperature, you know. What else do we know about incompressible materials?
Was it UT?
That's right. So specific internal energy is only a function of temperature. And then because of that, there's something we know about the specific heats. Remember what that is? So remember we have those two ugly specific heats that have partial derivative definitions. CV and CP are both we just call them C since they're the same for incompressible. For ideal gases, they're not the same, but for incompressible materials, they are. And this is just equal to the total derivative of U with respect to temperature. Okay, so that's what we have to work with. So let's go up to these TDS equations. None of these things that were given for incompressible say anything about H. So let's start with the one that talks about stuff we're given. You know what I mean? So there's no H. So we'll try the first TDS equation. Okay, and so that says that TDS is equal to du plus p dv. Okay, and let's see what we can make out of this using those assumptions. So first look at the second term. If v is constant, what's dv equal to? 0. You whispered it. Can't take it back. So this is 0 because dv is equal to 0. And then what about du? Well, we can rewrite du as c dt from that definition of specific heat for an incompressible material. So TDS is equal to C dt. Okay. And now we can divide both sides by t, and we get ds is equal to C dt over t. And now we can integrate both sides. So the integral from state 1 to state 2 of ds is equal to c times the integral from state 1 to state 2 of dt over t.
Where did the pressure go?
That second term is the pressure times the change in specific volume, but the change in specific volume is 0, so that whole term goes away.
And how did we get du into CDT?
From this.
Oh, that one.
So I just, multiplied both sides by dt. And so now when you integrate ds, you get the change in s. And if you integrate this one, you get natural log of the absolute value of temperature. But remember, this temperature is always positive. Well, so let me write it out. And this is evaluated from T1 to T2. Now, what about that absolute value? Well, T is always positive, so we can just write this as natural log of T from T1 to T2. because T is always positive when you're talking about absolute temperatures.
What about C? Do we?
I left that off like a stupid idiot. And so this is C times the natural log of, well, it's equal to C times the natural log of T2 minus C times the natural log of T1. And then the log rules say that we can write it like this, T2 over T1. And so if you want to calculate the change in entropy for an incompressible material, it's equal to C times the natural log of T2 over T1. And that's something we're going to use quite a bit, actually. This is for an incompressible material. Which is a liquid. So if we know two temperatures of liquid water, we can pretty accurately calculate the change in the entropy. Any questions about that? Okay, let's stop there. And I will give you some assignments for Wednesday that are related to, not the TDS equations yet, but related to the Clausius inequality. Okay, that's all.